Today, I would like to talk about ideal gas ensembles. I will start with an introduction to the ideal gas and the reminder of the ensembles that were discussed recently. Then I would like to discuss the thermodynamics of an ideal gas with different ensembles. At last, I will briefly talk about the non-ideal behavior of the gas. A simple and practical application of the equilibrium ensemble formalisms of the previous lecture concerns an ideal gas. Such a physical system is distinguished by the property that the system energy is independent of particle position, since the molecules are assumed not to interact through a long-range potential. Molecules do, however, collide, and this affects system not equilibrium behavior, as we shall see later. In the present context, we assume such collisions do not affect total energy. A system in which no collisions occur has almost the same energy as the realistic case in which collisions do occur. This weak interaction assumption works reasonably well for many gases in practical applications, and so they are termed ideal to a good approximation. Some brief remarks on deviations from this will be made at the end of the lecture. In order to illustrate the ensemble methods developed in the previous lecture, we perform calculations for the microcanonical ensemble as well as the grand canonical ensemble. Due to the fact that there was no lecture for a long time, let me briefly recall the ensembles that were discussed recently. Three different configurations have been considered. First, completely close to the environment. Here, conserved quantities for the dynamical system will be constant in time. Such a configuration is termed microcanonical. Second, open to exchanges of energy only with the environment. In this case, if the system reaches equilibrium, then the total energy will show very small fluctuations from a mean value. This is due to the energy interchange with the environment. Such a configuration is termed canonical. Third, open to exchange of energy and molecules with the environment. This is an extension of the previous case. Here, both the total energy and the number of particles will be subject to small fluctuation about means of both quantities. This configuration is termed grand canonical. From the microcanonical ensemble members lying on a submanifold of phase space, we know that there are some important mathematical technicalities which we will avoid for clarity. Heuristically, we can write the microcanonical density in phase space as proportional to 1 over reduced Planck constant to the power of 3n times the factorial of n times the Dirac delta function of the mean thermodynamic energy E0 over the reference energy ET minus energy E over the reference energy ET, and that is equal to the 1 over reduced Planck constant to the power of 3n times the factorial of n times the reference energy ET times the Dirac delta function of the mean thermodynamic energy E0 minus energy E. ET is a reference energy to ensure dimensional consistency, and energy E depends on the phase space variables. Now, in a distribution sense, we have that the Dirac delta function of x minus y equals the partial derivative with respect to x of the Heaviside step function theta of x minus y. The microcanonical partition function Zm is the integral over phase space of the microcanonical density D, since it is the normalization factor. The microcanonical partition function Zm equals the reference energy Et times the partial derivative with respect to the mean thermodynamic energy E0 of the integral of d to the power of np times d to the power of nq divided by the reduced Planck constant to the power of 3n times the factorial of n times the Heaviside step function theta of the mean thermodynamic energy E0 minus energy E. Consider now the integral of d to the power of np times d to the power of nq divided by the reduced Planck constant to the power of 3n times the factorial of n times the Heaviside step function theta of the mean thermodynamic energy E0 minus energy E, that equals In. For an ideal gas, energy E depends only on the momenta P of the molecules and not on their position Q. Note, though, that the gas is assumed to be confined to a particular volume, so the integrals over position result in a power of the confining volume V. We have, therefore, that the In equals the volume V to the power of n divided by the reduced Planck constant to the power of 3n times the factorial of n times the integral of d to the power of 3 p1 up to d to the power of 3 pn times the Heaviside step function theta of the mean thermodynamic energy E0 minus the sum from I equals 1 to n of pi squared over 2m. We are using the expression for the kinetic energy of a free molecule of mass m. Now we will use non-dimensionalizing the momenta using the mean thermodynamic energy E0. Non-dimensionalizing is the partial or full removal of physical dimensions from an equation involving physical quantities by a suitable substitution of variables. Let's substitute xi so that it is equal pi over the square root of 2m times E0. We obtain that In equals the volume V to the power of n divided by the reduced Planck constant to the power of 3n times the factorial of n times 2 times mass m times the mean thermodynamic energy E0 to the power of 3n over 2 times C3n, where this CD is identical to the integral of dx1 up to dxd times the Heaviside step function theta of 1 minus sum from I equals 1 to d of xi squared. Now, from the nature of the step function, the latter integral is clearly the volume of a hypersphere of dimension d and radius 1, which can be shown to be pi to the power of d over 2 divided by the gamma function of d over 2 plus 1, which gives pi to the power of d over 2 divided by the factorial of d over 2. Inserting this into our expression for In and differentiating this with respect to the thermodynamic energy E0, we obtain for the microcanonical partition function, which is equal to volume V times mass m times the mean thermodynamic energy E0 to the power of 3 over 2 divided by the reduced Planck constant to the power of 3, and all this to the power of n times 3n times the reference energy Et divided by n factorial times 2 times the mean thermodynamic energy E0 times the gamma function of 3n over 2 plus 1. The entropy S of E0 and V is simply the logarithm of this partition function, since the microcanonical density is uniform on the submanifold of constant energy. Now, the objects of interest thermodynamically are those which apply in the limit that n tends to infinity. That is, the number of molecules becomes very large. Of course, in such a limit, both the energy and entropy also become infinite. So we define energy entropy and molecular densities, which are epsilon equals the mean thermodynamic energy E0 over n, small s equals the entropy S over n, and small n equals n over v. This converge in the thermodynamic limit, and the straightforward computation, but a little tedious, gives for the entropy density or entropy per molecule small s equals logarithm of E to the power of 5 over 2 divided by small n times the reduced Planck constant to the power of 3 times 4 pi times epsilon divided by 3 to the power of 3 over 2. A result for ideal gases known as the Sakura-Tetrad equation. Notice that it does not involve the reference energy ET. Furthermore, it is also the result of taking the thermodynamic limit. The expressions for a finite number of molecules are complicated functions of n. Note finally that the ideal gas simplification allowed the computation to be reduced to that of computing the volume of a hypersphere. If this simplification had not occurred, the calculation would have been potentially considerably more difficult. The computation in the previous section involves hypergeometry, and the result for the partition function is a rather complex function of n, the number of molecules, and requires the thermodynamic limit to interpret clearly. Canonical ensembles are usually easier to work with. In the last lecture, we computed the partition function zg of lambda 1 and lambda 2 that is identical to the sum from n equals 0 to infinity of the integral over r to the 2n of exponential of minus temperature T to the minus 1 times the energy E plus me times temperature T to the minus 1 times the number of molecules n dV. In this equation, dV equals d to the n p times d to the nq divided by the reduced Planck's constant to the 3n times the factorial of n. We can write that lambda 1 equals minus temperature T to the minus 1 and lambda 2 equals the chemical potential me times temperature T to the minus 1. The integral over phase space can be carried out rather easily for an ideal gas because energy E equals the sum from I equals 1 to n of momentum pi squared over 2 mass m. Thus, it does not depend on the position of molecules, and the dependency with respect to momentum results in a Gaussian function. The position integration results in a factor of v to the power of n, while the momentum integration of the Gaussian gives a factor of 2 pi mt to the power of 3n over 2. Hence, the partition function zg equals the sum from n equals 0 to infinity of 1 over n factorial times v times exponential of me times temperature T to the minus 1 times 2 pi mt to the power of 3 over 2 divided by the reduced Planck constant cubed and to the power of n, which is a Maclaurin series for an exponential function. So this partition function zg equals e to the power of v times e to the me times t to the power of minus 1 divided by the length scale L cubed, which is this L is the quantum wavelength of a molecule of energy and is called the thermal wavelength. And thermal wavelength is identical to the reduced Planck constant times square root of 2 times pi divided by mass times temperature, and is equal to the reduced Planck constant times square root of 2 pi divided by mass times the square root of minus lambda 1. The given expression presages simple thermodynamic relations for an ideal gas. From the next equation, it can be derived that the mean n equals the partial derivative of the logarithm of the partition function with respect to the lambda 2, and E0 equals the partial derivative of the logarithm of the partition function with respect to the lambda 1. And hence that the mean n equals v times e to the mi times t to the power minus 1 divided by the length scale L cubed. Since the particle density small n equals the mean n over v, small n equals e to the mi times t to the power of minus 1 divided by the length scale L cubed. Likewise, the thermodynamic energy can be derived from the derivative of the partition function. Thermodynamic energy E0 equals v times exponential of lambda 2 times the partial derivative of the length scale L to the minus 3 with respect to the lambda 1, and that is equal to v times exponential of mi times temperature T to the minus 1 times 1.5 times temperature times length scale to the power of minus 3 equals 1.5 times mean n times t. Similarly, the energy per particle epsilon equals thermodynamic energy E0 over mean n, and that is equal to 3 over 2 times temperature T. Now, the entropy for the grand canonical ensemble may be derived in the same way we did in the last lecture for the canonical ensemble, obtaining the modified relation. Entropy S equals temperature T to the minus 1 times thermodynamic energy E0 minus the chemical potential mi times the temperature T to the minus 1 times mean number of molecules n plus logarithm of the partition function zg. From lecture 3, we know that pressure PR over T equals the partial derivative of S with respect to V, and that is equal to the partial derivative of logarithm of the partition function Zg with respect to V. We can present the pressure in the form PR equals particle density small n times temperature T. Another well-known ideal gas equation, sometimes called the equation of state. Now, from given equations, we can derive an entropy density equation. So entropy density or entropy per molecule, small s, equals entropy S over mean number of molecules n, and equals 5 over 2 minus the chemical potential mi over temperature T. We can also obtain the chemical potential mi that is equal to 2/3 times epsilon times logarithm of n times L cubed. We can transform now the form of entropy density to the logarithm of E to the power of 5 over 2 divided by n times L cubed. When the definition of L is used, we can see that this is the same equation we derived earlier using the microcanonical ensemble, the Sakura Tetrad equation. Notice how the grand canonical ensemble calculations were able to rather rapidly access much of the thermodynamics of the ideal gas. This is in contrast to the rather cumbersome and limited microcanonical calculation. Note for that they coincide in the thermodynamic limit. The ideal gas assumption ignores the energetics of molecular interactions. Under certain circumstances, collisions between molecules can become significant. This is dealt with by introducing a potential function which varies with the distance between any two particles, where multiple collisions are extremely rare. This potential function modifies the energy equation by the introduction of a function depending on molecular positions. The exponential of this function must then be integrated over with respect to any two molecules. In the ideal case, the molecular position integrals simply resulted in a factor of v to the power of n. With the potential function, this is modified in such a way that depends on the gas temperature T, and this additional effect modifies the usual ideal gas equations. An introduction to these effects will be discussed next time. With this, I would like to end today's talk. Thank you.